All right, I wanted to work out last example with you. So we're going to do a work problem. We're going to move a particle from negative 2, 0 along the x-axis and then up around the semicircle back to where it started. So maybe we should sketch a picture first. What are we looking at? So our picture looks like this. We're starting here at negative 2, 0. We're going to 2, 0. We're going like this. And then thankfully the semicircle is actually the top half of the circle of radius 2. Mine's a little crooked, but hopefully you can make it work. If not, I'm very sorry. And let's realize that the work done here by this vector field and moving the particle, the work is just the line integral along C. By the way, C is simple, and it's closed, and it has positive orientation, so we might as well put the little circle on it. So it's the line integral along C of f dot dr. That's the big interpretation you need to make. And I'm looking at this and I'm thinking, man, this will be a great region for a double integral because it looks like something that would be very nice for polar. So I'm motivated to try out Green's theorem. Before I do that in my mind, I'm going to check and see whether this vector field is conservative or not, because if it is, I'm done. It's not conservative, so we'll go ahead and proceed. And so I know by Green's theorem I can write this as the double integral over D, where D is the region inside C. D of, and then it's going to be what? Q partial x minus P partial y dA, where maybe we should write this a little more standard. This is what? X cubed plus 3x y squared. So this is my P and this is my Q. And so I'll let you switch this. And so we're going to get the double integral over D of what? Q partial x is going to be a 3x squared plus 3y squared. And then I'm going to have a minus P partial y, which is just 0. So I get just that dA. And boy, this is just begging to be switched to polar coordinates. So we can see the r is going from 0 out to 2. Theta is swinging around from 0 to pi. And so this is just going to be the integral. R goes 0 to 2. Theta goes 0 to pi. And gosh, this is just a 3r squared times r dr d theta. And I'll let you work out the details. It's pretty straightforward. You just get 12 pi. So this problem was not bad at all. I wanted to end this lecture series by making a couple of connections with you. So one of them is this interesting tool called I'm not sure actually how you pronounce it. I think it's a planimeter. Google it if you want to. I believe it's spelled like this. I'm not sure how to cite pictures on here. I would definitely want to do that. This picture came from the AMS website. But basically, a planimeter is a tool where if you take this part of it and you trace out a curve, then you actually are able to compute the area of the curve using this tool. They're really interesting. They've been around for quite a while. Nobody quite could prove why they worked until somebody made the connection with Green's theorem in the 1940s, and you can read all about that if you want to YouTube it. But just to show you what we're talking about whoops, I'd like to actually draw this. We have this curve C, and we're able to take an integral over its boundary, entirely in terms of the boundary, just the curve itself, and we're able to translate that to the area of the region using double integrals in Green's theorem. So really interesting idea. One more thing, notice that we're able to go the other way now. Let's think about the double integral of Q partial x minus P partial y dA over D. So now I'm going to think about double integrating over the inside, and I'm able to change that to an integral entirely over the boundary. And that's a interesting idea that you've actually already seen before back in Calc 1, and I want to show you why really quickly. So we took the integral over a function, f of x, from a to b. All right, so we had this complicated, well, it wasn't too complicated necessarily, depending on the function. We had this integral from a to b of f of x dx, and we were able to express that as big F of b minus big F of a. And what you might not have realized at the time was I'm integrating over this closed bounded interval, and the boundary of that interval, if you're going to talk about the boundaries of this interval, the boundary is a and b. And so I was able to translate the integral over the whole thing to an expression involving a function and boundary points, right? Just the boundaries here, which is a and b. And well, that's very similar to what we're doing here. We're taking a double integral over this whole region, and we're able to express it as a smaller integral, so to speak, a different integral over just the boundary. And that idea of going from a larger object to its boundary, we're going to see 2 more times in 2 different theorems. So wanted to try to make that connection clear to you. That's the fundamental theorem of calculus showing up again in some sense. So we'll stop this video here. You've got everything you need to do to knock out 13.4, and if I have time this evening, I'm going to post a Exam 3 comments video